So, the overall goal of this project is to build a machine learning model that is able to predict an individual's annual income if it exceeds $50,000. And so far, I have made sure to build a solid foundation for my model building. And this included dataset exploration, cleaning, analysis, and preprocessing. I covered all of these parts in 4 previous videos. If you have not watched any of them, I encourage that you do because it provides great context and basis for what I am about to do. So far, I have already introduced all of these inputs in the previous videos, and let me focus on the ones that I haven't introduced that we'll be using for building our models. So we've already established that this is a classification supervised machine learning problem, and I'll be using traditional or classical machine learning algorithms, no deep learning here. So I made a selection of linear and non-linear, simple and complex algorithms for this project. So the algorithms that I chose were logistic regression, random forest classifier, support vector machine classifier, and XGBoost classifier. Also, XGBoost is not installed by default in my Anaconda Jupyter environment, so I had to make sure to install XGBoost here first before importing anything from it. Here are the evaluation metrics that I'm going to be using to evaluate my models. And when we get into evaluating these models, we get to see why we are considering all of these metrics and not just one. So a quick overview of what happened in our preprocessing pipeline. I discussed this deeply in the last video. So first, I separated my data set into my features and my target. So my target is not going to be needing any of these preprocessing steps here because the values inside are already zeros and ones. I made sure that I replaced all of the less than or equals to 50k with 0 and greater than 50k with 1. I already did that in the dataset cleaning. So the preprocessing that I'll be doing here is going to only be applied to my features, which is the X. So I carefully stated out all the preprocessing steps in a pipeline. Also, I did not fit the pipeline to the entire features. First, I split my data into the test set and the training set. So the training set is 80% of the data, and then the test set is 20% of it. Then what I fit to my pipeline is the X train. Then whatever it learns from the X train, I use it to transform my X train and my X test. So I made sure that my X test was not fitted to the pipeline in order to avoid data leakage. So the data now that is getting into my model, or that I'll be using to build my models basically, is my X train processed, X test processed, and then my Y train and my Y test. So that's what I'll be using to build my models. Getting right into building the models, so I'm going to be having baseline models and tuned models. The baseline models, I'm using these algorithms that I have already introduced. I'm using them in their default state without tuning any hyperparameter. Why am I doing this? First is it gives me a good idea of how well my preprocessed data is, and secondly, it gives me an idea into what I should be tuning so that I don't have to be tuning my models blindly. Let me use the default state of these algorithms first and then see what the result is like. And then whatever is lacking, that is what I would be improving on when I am tuning my models. So the approach I took for this is first I created a function that would help me fit my model, make predictions, and make evaluations so that I don't have to repeat this over and over for every algorithm. So my function evaluate model, it takes in whatever model that I have already defined. It takes in my train data set, it takes in my test data set, it fits the model to the train data set, and then it uses the test data set to make predictions, to test it and evaluate it, and then it computes all of these evaluation metrics for me. It gives me their result, and then it also gives me a confusion matrix and ROC curve for each model that I put into the function basically. And then here I'm asking it to return this because at the end of the day, this is what I'm going to be using to compare all of the models. So getting right into building my models, I am starting with logistic regression. And logistic regression really is that simple linear model that gives me a good, benchmark. It may not be able to cover non-linear and complex relationships well, but I have other models for that. So let's just see how this is going to perform. Here I created an instance of it and I made maximum iteration 1000 for convergence, and this is me running my logistic regression into the function that I have already defined, and we also have an understanding of all of this, the data that is going into it. Now, looking at the results that I'm getting from my logistic regression, accuracy is standing at 83%. And looking at it overall, it seems like, oh, this is great, right? But accuracy is something that we have to be very careful with, because it can be very misleading with the data sets that we're dealing with, especially if the data set is imbalanced. Like in this project now, 75.5% of the people in this data set belong to the less than or equal to $50,000 annual income, and then only 24.5% of the people belong to the greater than $50,000 annual income, right? So even if the model is able to correctly predict all of the people that belong to the zero class, that's less than or equals to 50K, it's already going to show us about 75%, which is very, very misleading. That's if the model is able to only predict the people in the less than or equals to 50K class alone, and is not able to get any of the ones correctly in the other class, it's going to be very misleading, because it will be showing 75% already. So that is why we're also considering other evaluation metrics. So the question that accuracy answers, accuracy simply answers the question that what is the proportion of all of the correct predictions that the model made. So regardless of the class, accuracy is just saying like how many correct predictions did the model make, right? Now for precision, the question that precision answers is of all of the correct predictions for the positive class that the model made, how many are correct? So precision is more about the correctness of the predictions for the positive class. Precision prioritizes being correct. So precision doesn't pay so much attention on if the model gets all of the positive class or not. It's just saying that if the model says this number of people belong to the positive class, then they should all belong to that class, or at least only a very number should not. So precision is about the correctness of that. Now recall focuses, or recall answers the question of all of the people in the data sets that actually belong to the class greater than 50K annual income, right? How many of them is the model able to capture? So recall prioritizes the model being able to capture as many people in the positive group as possible. So recall prioritizes sensitivity of the model to this. So F1 score is simply the harmonic mean between precision and recall. And of course, we want to have a very good F1 score, right? A balanced F1 score. But somehow we are a little bit biased to recall in this project, because we want our model to be very sensitive to the positive class. And ROC-AUC simply measures how well our model is able to differentiate between the two classes across like multiple thresholds, right? So looking at this confusion matrix, I'll use it just to explain this metrics also a little bit more. Also, so we are not confused, whenever I say like the negative class or class 0, I'm referring to people that belong to the less than or equals to 50K, and whenever I say the positive class or class 1, I'm referring to all of the people that belongs to the greater than 50K, right? So now this diagonal we're seeing here, this is our correct predictions. Now this value that we're seeing here is our true negative. So the rows here represent the actual values, and then the columns here represent the predicted values, right? Now this intersection here is the number of people that, yes, they actually belong to the class 0, and the model correctly predicts them to belong to the class 0. So this is the true negative. And then this is our true positive, the people that actually belong to the class 1, and the model predicted them to be in class 1, right? So this diagonal here is for our correct predictions. This off diagonal here is for the incorrect predictions, basically. This here is our false positive values. That's the people that they actually belong to the class 0, but the model predicted them to belong to the class 1. So it means that they actually belong to the less than or equals to 50K, but the model predicted them to be greater than 50K. So this is false positive, and this value here is our false negative. It means that the people actually belong to the class 1. So these people here, they actually earn greater than 50K, but the model is predicting them to be earning less than or equals to 50K. So what I'm getting from this is that, first of all, our model is not very sensitive because the recall is low, right? So if we're going to tune these models, we have to prioritize the recall as our evaluation metrics. Also, our aim in tuning these models is to reduce these values here. We want to reduce as many false negative, as many false positive, and as many false negative as possible. Also, what precision does is precision tries to minimize the number of our false positive, and recall tries to minimize the number of our false negative. So let's consider, and then here we can see our AUC value is 0.89, and the closer it is to 1, the better it is that, you know, it's able to differentiate between these classes. So quickly looking at our random forest, we can see the results here. So the accuracy is a little bit lower than that of logistic regression, but the recall is slightly higher than that of logistic regression. So we can see that the random forest is slightly more sensitive compared to our logistic regression. And then looking at our XGBoost and running it, the results from it, we can see that XGBoost so far is the best performing model. It has an accuracy of 86.7%, and we can see the recall is way better than the others, right? But we can see that we can also still improve it, because false positive and false negative, we still need to reduce this number, you know, and make it better. And it's no surprise that XGBoost is giving us this, you know, better performance, because XGBoost and random forest, they both use decision trees, right? But random forest uses these decision trees. All of the decision trees are like independent, they are in parallel using bootstrap samples, right? And at the end of the day, it just averages the result from all of these decision trees. But XGBoost is a boosting method, right? That it is a boosting method basically, but the way it arranges the decision trees is that it is in sequence. So each decision tree is using the result from the one before it, and then it makes it better. It helps to improve and reduce the errors from the one before it. So that is why XGBoost is giving us this great result. And then what I also did was to get the feature importance for my XGBoost. So far, it's the best performing model, and I just wanted to see the variables that influence the decisions or that influence the learning of my XGBoost. And why I'm doing this is during our exploratory data analysis, there were some patterns that I noticed, you know, some features that were more correlated to our income group, and I wanted to see if it's the same thing that is being reflected here in my model, if the model is learning more from those variables, right? If it's learning from those variables, it means that everything, you know, is in alignment. But if it is learning from some variables that I had not seen to be highly correlated with my income, then that would give me a good hint to do more investigation. You know, some variables may not show great correlation standing on their own, but when they are combined with others, they may show great correlation. And that's basically what I did here. And so far everything is aligning, because the marital status, education, capital gain, capital loss, all of these variables, you know, they had like high correlation and great influence on my income during our exploratory data analysis. So I simply had a bar chart here to compare them, to simply have their feature importance scores, and I'm seeing that everything is aligning as it should. I have the summary of that, and then also I decided to use support vector machine because it gives like a different approach to the whole thing. Yeah, so my support vector machine, basically it looks for like the best boundary or margin between like these classes, and with a kernel like this that I'm using here, and with a kernel like this is able to get really you know, more complex and non-linear relationships. But comparing it with the other models, we can see that it is actually not even far from logistic regression and random forest. So far my XGBoost is the best performing model among all of these models that I have trained. And simply what I did here was I went ahead to compare all of the models. So I have a combined ROC curve for them here, and then I also decided to simply have a data frame that binds or compares all of them really across all the several metrics that we've considered, and I have a summary here of them here. So what we've understood from this is that when we're tuning our models, we have to tune it in such a way that we are improving the sensitivity of these models so that they're able to capture more of the positive class. So that's all for the baseline models. The next video is going to be on the tuned models. Stay tuned.